Unit 4 Chemistry, Chapter 12, looking at now at how we can analyse these organic compounds using a range of different spectroscopic techniques. This first video we will focus on infrared spectroscopy only. So, infrared is very important because it can identify the functional groups. Okay? So it can identify whether you've got carboxy groups or amine groups, and it can also identify the presence of alkyl groups. Okay? We can also tell us whether we've got single, double or triple bonds in there. So it's a very useful technique for telling us what type of arrangement of atoms we've got in there. It works because molecules that have got asymmetrical bonds are able to absorb infrared radiation. And just like we remember back in Unit 1, we said that when electrons absorb radiation, they go to a higher energy level. Well, that was for visible light. These ones, they absorb infrared radiation, and that changes the bond to a higher energy level. You don't need to know the details of what type of stretch or change they do, just that it changes how they're moving, and it goes to a higher level. Okay? The bonds are only able to occupy what we say discrete energy levels. What that basically means is they will absorb a set wavelength of light in order to change that. So we can use that wavelength to identify what type of bond is there. Okay? So a carbon-carbon bond will absorb a wavelength of around 850 centimeters to the -1. Don't worry about the units, just accept that's what it is. What exact wavelength they absorb, okay, or frequency and wavelength are the inverse of each other, so we can talk about one or the other. The frequency is dependent on how heavy the atoms are and the distance between the atoms, so the length of that bond. Okay? And here are some examples of the bonds and the frequency that they absorb at. Okay? And we can see that when carbon is bonded to a lighter one, we get a higher frequency, and as it's bonded to heavier and heavier and heavier atoms, we are getting a decrease in the frequency. Okay? So what we're doing, we've got it in its lower state, we add energy, and it transfers it to a higher state. And it works for all molecules except those which we'd call homonuclear, meaning they've got the same nucleus on both sides. So that's like your diatomic gases. Yeah, H2, N2, Cl2, that's not going to absorb IR. Everything else will, if it's got a covalent bond in it. Okay? When we look at an IR spectrum, it's going to look upside down compared to the ones you would have seen last year, your UV Vis or your AAS. Okay? So it's got a baseline that says 0 absorbance, and it dips when radiation has been absorbed. So it looks like this. So this is our baseline. That means it's not being absorbed. And when we see a dip like that, that means there is a bond there that absorbed that particular wavelength or frequency of it. And another one here. Okay? We divide it into 4 parts. Okay? The most useful part that you're going to be looking at normally is on the far left, and that's where you always want to start, because that's where you'd find bonds characteristic of an amine group, bonds characteristic of OH alkanol and of OH acid, and those two different ones actually give us different things. Okay? We will look at these green and blue regions too, because we've got C-double bond O's there, which might tell us we've got an ester, or it might tell us we've got an amide rather than an amine. Okay? We might also see this one here, so we might have triple bonds or double bonds being evident in these regions. What we're not going to look at is this pink region here. Okay, it's called the fingerprint region, and yes, it does have some useful bonds in it, but we can work out those functional groups based on other bonds that are up here. The reason we can't use that is because in that region the whole molecule bends and stretches. So if we see a trough in that region, we don't know if it's due to one of these bonds or if it's due to the whole molecule having a bit of a wiggle around. Okay? That means that really this one and this one, we're not going to be able to look for those bonds at all. So even though that data may appear in your data book, it's kind of a distractor. It's kind of almost trying to pull you into a trap and look for it and use it. Don't fall into that trap. Anything below about 1400 is useless to you. Okay. Now we can use IR for qualitative and quantitative analysis, and we normally use it for qualitative to tell us what is present. Okay. So we would look for certain stretches. So here, for instance, we might see an OH alkanol stretch. We might see a CH stretch. Now, a CH stretch is always going to be there. Every organic molecule has got carbon-hydrogen bonds. Okay? But you need to look for it because you need to make sure you don't mistake it for something else. So you need to go, yep, that one's there. Now, what else have I got? Okay? We'll see a range of different molecules. So we would see in an acid, for instance, this nice broad peak, and you're also going to see a C double bond O. Whereas if it's an ester, you've just got that C double bond O, and look, here's your CH. These little wiggles here are not significant. Okay, little wiggles like that, we're not looking at. Big troughs, that's what we want to look for. Okay. So anytime you see an ester, you're going to see a CH bond, and then you're going to see a deep C double bond O. Okay? You're not going to see anything other than a CH up here. If it's a carboxylic acid, however, you will see that C double bond O, but you'll also see this big, huge, really spread out one, which is a bit of a double peak. So you've got a drop here, which is your OH acid, and then a little mini peak there, and that's your CH. Because your OH acid was so big, it overlapped with it. Okay? This is a very strong characteristic sign that you have got a carboxylic acid there. Alkanols have also got OH, and it's also a big peak, but it's going to be completely separate from your CH. So here's your CH, here's your OH alkanol. If ever you're writing what bond you found, you have to say OH alkanol or OH acid. And look also, the other reason we know it's an alkanol, there's no CH bond there. Sorry, there's no C double bond O bond there. The CH bond, of course, is there. We can also use IR for quantitative analysis, but that's much, much rarer. Okay? What we basically know is that the more of those bonds there are, the stronger the signal's going to be. So if we see a really deep peak, then we know that there are lots of that type of bonds. If we're doing a side-by-side comparison, and we see one peak is bigger than the other, then we can say, and it's the same type of peak, then we can say that that one has more of the bonds than other. So it might be useful if you're trying to compare something which has one OH group to something which has two. You do a side-by-side comparison. The one with the deeper OH alkanol one is going to be the one which has the diol group, or two OH groups. Okay. You could also construct a calibration curve based on the depth of these peaks. I've never seen that type of analysis come up in a VCAR question, but it's possible that they could do that if they gave you the depth or the area of the peak.